Okay, today we're going to derive the expression for relativistic momentum, starting from the Lorentz transform for a velocity that is perpendicular to the relative velocity of two reference frames. So let me begin by reminding you what I mean by that. If we have a reference frame S, and here's an observer in that reference frame, and there's a different frame S prime, which is moving, so this is S prime, it's moving to the right at speed v relative to S. And there is some object, let's say a bird in S prime, so here's the bird, and it's traveling with a diagonal velocity. So I'm defining in both reference frames y to be the vertical axis and x to be the horizontal axis. So the components of velocity of the bird as seen in S prime are u sub x prime and u sub y prime. And the Lorentz transform for velocity allows us to deduce what the components of velocity will be for the bird as seen in frame S, that is, what is u sub x and u sub y. And as we have shown previously, we get the result that u sub y equals u sub y prime divided by gamma times 1 plus u sub x prime v over c squared. Okay. So armed with this, let's consider the following thought experiment. In frame S, I imagine taking a ball, so here's my ball, it's a blue ball, and I'm going to throw it vertically upward with a speed of u naught. So I'm going to call this ball A, and I'm going to throw it in the positive y direction with a speed u naught. In a separate experiment, and we'll tie them together soon, but for now think of this as being completely separate. In frame S prime, I'm going to have a ball that's identical in mass to ball A, but it's red instead of blue, and I'm going to throw that ball, which we'll call ball B, downward with the same speed u naught. These balls are identical. Each ball has a mass m naught. Now we're going to connect these two experiments by arranging that the balls collide in the middle. So let's look at this situation as seen in frame S. Here is ball A. It's going to go up and have a collision and then come straight back down. Here is ball B. It has a horizontal component of momentum because of the fact that S prime is moving relative to S. Remember, in frame S, it's stationary, so in frame S, its trajectory would look like this, straight down, collision, straight back up. But because of the motion of S prime, sorry, that was the picture in frame S prime. It goes straight down, collides, and straight back up. But in frame S, it has a horizontal component of momentum because frame S prime is moving relative to S prime. So the whole collision looks like this, collision, and then back. Again, ball B is moving diagonally because it has a vertical component of momentum from being thrown downward by the people in S prime, and a horizontal component of velocity from the relative motion of S prime to S. So again, the collision as seen in S prime, the collision as seen in S looks like this. And we could represent that in a picture as follows. So as seen in S, we would say that ball A goes straight up, has its collision, and comes straight back down, whereas ball B is following a diagonal path. So ball B is going like this, having the collision, and then going diagonally back up. This same sequence of events, we can portray it in frame S prime. And as seen in S prime, ball B would go straight down, collide, and straight back up. Ball A has a velocity to the left because frame S is moving to the left relative to S prime. So the collision in S prime would look like this. And we could draw it with ball B going straight down, having the collision, and then straight back up. Meantime, ball A is going diagonally right to left, colliding, and then coming back down. Sorry, this is A. Now, we've set things up so that things are very symmetrical between the two reference frames. And that means that there can be no transfer of energy from ball A to ball B or from ball B to ball A because there's nothing that distinguishes one frame from the other. So the symmetry of this situation guarantees that there's no transfer of energy from A to B or from B to A. We are also going to require that this is an elastic collision, meaning that there's no conversion of kinetic energy to heat. If you combine those two conditions, you can see that the only way to satisfy conservation of energy is that the rebound speed of each ball must equal its incident speed. Meaning, for example, before the collision, the upward speed of ball A is u0, so I could say u a y, the speed of ball A in the y direction, and there's no prime on this, so this is as observed in the S frame, is equal to u0. After the collision, it has to have the same kinetic energy because it didn't transfer any energy from ball B or to ball B, and there was no energy converted to heat, so the only way that we can arrange that is afterwards it has to have uay equals minus u0. Similarly, before the collision, we can break down the velocity of ball B into a vertical and a horizontal component. The horizontal component, ubx, the velocity of ball B in the x direction, no prime, so that's as measured in S, that's due entirely to the velocity of frame S prime relative to frame S, because in S prime, ball B is moving straight up and down. So ubx is simply equal to the velocity, capital V, of S prime relative to S. And that's unaffected by this collision because we set things up so that the forces are only in the vertical direction. So afterwards, we would also have ubx equals V. And we've got some vertical component of velocity before the collision, uby, and that's just going to get turned around. So afterwards, it has to have the same magnitude as it did before. Okay. First concept test. Before the collision, is the magnitude of the velocity of ball B in the y direction as perceived in frame S, so that's uby, that is to say this velocity, does that have a magnitude that's greater than, less than, or equal to the magnitude of the velocity of ball A in the y direction? That is to say, is this vector, which represents the y component of the velocity of ball B before the collision, greater than, less than, or equal to the length of this vector representing the velocity of ball A before the collision? I'm going to give you a hint that you should use the Lorentz transform for velocity and apply this to ball B. So I want you to think about this on your own, pause the video, When you're ready, unpause the video and we'll talk about the solution. Okay, so following the hint, we apply the Lorentz transform for velocity to ball B. So that's going to tell us that u by is equal. So this is the Lorentz transform. Tells us that u by equals u by prime divided by gamma times 1 plus u bx prime v over c squared. U by prime, that's the velocity of ball B before the collision as seen in the prime reference frame. So that would be negative u naught because it's going down, u by prime. U bx prime, which is the velocity of the ball in the x direction before the collision, is just 0 because it's going straight down. So u bx prime is 0. So that means that u by is equal to minus u naught divided by gamma. Recall that uay is u naught. U by we just showed is minus u naught over gamma. Gamma is a number that's always greater than or equal to 1. So that tells us that the magnitude of u by is less than the magnitude of uay. So the correct answer is less than. And I've tried to show that graphically, that this arrow is a little bit shorter than this arrow. Okay. Next concept test. If we define the momentum in the way that we're accustomed, that is, we say that vector p is equal to the mass, which in this problem we're calling m naught, times the velocity of the object, vector u, then before the collision is the total momentum of the system in the y direction, and there's no prime on this, so this means as seen in S, and total means we're combining both ball B and ball A, is that total momentum in the y direction greater than, less than, or equal to 0 before the collision. So again, pause the video, think about this on your own, and when you're ready, unpause the video. Okay. So we just showed that the magnitude of the y velocity of ball B before the collision is less than the magnitude of the velocity of ball A. Ball A is traveling in the positive y direction, ball B in the negative y direction. So that means that using this definition, the total momentum before the collision would be positive. All right, now let's think about after the collision. After the collision, ball A is moving downwards, ball B is moving upwards, but everything is symmetrical. We've already argued that the length of this vector has to equal the length of this vector. So now the total momentum would be downwards, the total momentum in the y direction. So before the collision, positive momentum. After the collision, negative momentum. That means that momentum is not conserved if we use this definition. Now that should be a bit of a shock. Conservation principles are the most important things in physics. In fact, we physicists like them so much that we're willing to make little tweaks, if necessary, to preserve the conservation principle rather than just abandoning it. So I'm going to make a claim, and let me move this paper to get myself more space to make my claim with. We'll keep the diagrams of the collisions on there, but start a new piece of paper here. Oh, before we start that, let me write down our result. U by we showed was minus u naught over gamma. So let me add that to our diagram here. UBY is minus U naught over gamma less than U naught, which is equal to UAY. Okay, so get a little more working space here, but keeping that diagram in place. I'm going to make the following claim. We can get conservation of momentum to work if we say that the mass increases with the speed of the object. Now that's a very peculiar idea, that the mass should depend on the speed, but let's see qualitatively how that could perhaps fix things for us, and then we'll do it quantitatively. Note that UB, the speed of ball B as seen in frame S, has both a y component and an x component. Therefore, there is the possibility, and we'll show this presently, that UB might be greater than UA. We know that UBY is smaller than UA, but we have to add in the effect of the horizontal component. So maybe this vector representing the velocity of ball B, the total velocity, could be longer than this vector representing the total velocity of ball A. If the mass increases with speed, that means that B would have a larger mass than ball A, and perhaps that larger mass could compensate for the smaller velocity in the y direction, so that the total momentum of ball B in the downward direction might be equal to the total momentum of ball A in the upward direction, giving you a zero total momentum before the collision, and then everything just reverses after the collision, so if the momentum was zero before, it would also be zero afterwards. So that's qualitatively how this is going to work. It requires, if that's going to work, we have to have that UB is greater than UA, which is just equal to U naught. So let's check that. So again, qualitatively, if the total velocity of UB is greater than the velocity of UA, then that would mean the mass of ball B was greater than the mass of ball A, because of this strange idea that the mass might just depend on speed. And so that could mean that the total momentum, that the y component of momentum of ball B could have the same magnitude as the y component of momentum of ball A, because the larger mass could compensate for the smaller y component of velocity. So let's check first whether this is true, whether the velocity of ball B really is greater than the velocity of ball A. And we'll do a little bit of algebra, but it will come in handy later on. So UB, using Pythagoras, is equal to the square root of UBY squared plus UBX squared. And if I substitute for UBY as minus U naught over gamma, and for UBX as V, and I'm also going to square both sides of the equation, that's going to give me on the left side UB squared equals UBY squared, which would just be minus U naught over gamma quantity squared, plus UBX squared, which is just V squared. Remember that gamma is defined to be 1 over the square root of 1 minus V squared over C squared. And so if we plug that into this equation, when I square it gets rid of the minus sign. So UB squared is equal to U naught squared times 1 over gamma squared, which is 1 minus V squared over C squared, plus V squared. And now I'm just going to rearrange those terms a little bit. So that's equal to u naught squared plus v squared times 1 from this minus u naught squared over c squared from this term. Now we're assuming that the balls are traveling at a speed u naught that's less than the speed of light, and so that means that this quantity, 1 minus u naught over c squared, would be greater than 0. And in turn, so if I'm taking u naught squared, adding it to v squared times a positive coefficient, this is going to give us a number that's greater than u naught squared. And UA is just u naught, and so that tells us that UB is greater than UA, which is what we wanted. Okay. So the one result from all of this that we're going to need going forward is that UB squared equals this. So I need some more space, so I'm just going to transfer that up here. UB squared equals u naught squared plus v squared times the quantity 1 minus u naught squared over c squared. Okay. So now let me get myself some more space to work with. I'm going to make the following claim about the exact way in which the mass depends on the velocity, and then we'll show that this works. So my claim is that the particular way in which the mass needs to depend on velocity is that we're going to use, instead of just the mass that we measure when the object is at rest, we're going to take that so-called rest mass, again the mass measured when the object is at rest, and multiply it by gamma sub u, where gamma sub u is just like our normal gamma, but we replace the v with the u. So gamma sub u is equal to 1 over the square root of 1 minus u squared over c squared. And so you can see that that gives us a mass that increases as the velocity increases. So if we use this definition, that means that the momentum, instead of simply being m naught times gamma, would be m naught times gamma sub u. I'm sorry, instead of being m naught times u, would be m naught times gamma sub u times vector u. So let's apply this claim to our situation here and see if it allows for momentum to be conserved. Before the collision, we have that the momentum of ball A in the y direction is equal to, using our new expression, the rest mass of ball A, which is m naught, times the gamma appropriate to ball A, which would be gamma sub u naught, times the speed in the y direction of ball A, which is just u naught. Meantime, the momentum in the y direction of ball B, as seen in S, because there's no prime on this, would be the rest mass of ball B times the gamma appropriate to ball B. Now gamma depends on the speed, not on the component of the speed that you're considering here, right? There's no u sub x here. It just depends on the magnitude of the speed. So I'm just going to write gamma sub u sub b here, but the component of the momentum in the appropriate direction, as you can see from the vector nature of this equation, depends on the corresponding component of the velocity. That is, in this case, I want u by. Now we already know that u by is minus u naught over gamma. And we know that gamma sub u sub b would be 1 over the square root of 1 minus ub squared over c squared. And here's where we're going to make use of what we know about ub squared from the algebra that we did before. So if I plug that into this definition, I'm going to get that gamma sub u sub b is equal to 1 divided by the square root of 1 minus ub squared over c squared. So to start off with, that gives us a minus u naught squared over c squared, a minus v squared over c squared, and then finally minus v squared u naught squared over c squared, and there's another factor of 1 over c squared here, so it's going to be plus v squared u naught squared over c to the fourth. And all of that is underneath a square root sign. If you look at this carefully, you can see that the material underneath the square root sign can be factored. So I can factor this into 1 minus v squared over c squared times the quantity 1 minus u naught squared over c squared. Let's just see quickly how that works. The first 1 times 1 gives me 1. The outer 1 times minus u naught squared over c squared gives me this term. The inner minus v squared over c squared times 1 gives me this term. And the last, this times this, gives me that term. Okay. So that means that gamma sub u sub b is equal to 1 over the square root of 1 minus v squared over c squared times 1 over the square root of 1 minus u naught squared over c squared. But this we recognize as our regular gamma, and this is gamma sub u naught. So again, all of that is gamma sub u sub b, so plugging that into this equation gives us that p by equals m naught times gamma ub, which is gamma u naught, times minus u naught over gamma. I can cancel the factors of gamma, and I get that pby is minus m naught gamma u naught, which is exactly opposite pay. And that's what we wanted, because that means that the total momentum before the collision is 0 in the y direction, p total in the y direction before, which is pay plus pby equals 0. And as I argued before, after the collision, the velocities just reverse. And so if the sum of the momenta before the collision is 0, the sum of the momenta after the collision will also be 0. So similarly, after p total y is equal to 0, and so the momentum is conserved. So we've seen that this correction to our definition of the momentum really does work. So let's put this new definition of momentum in a starred box, and let's talk briefly about the interpretation. There are two different ways that different physicists interpret this. One is to say that the original definition of momentum, p equals m naught u, was just wrong, and you have to add this correction factor, gamma sub u, in order to make a right definition. The other way of thinking about it is this way, where we actually say, no, the original definition, mass times velocity, wasn't wrong. It's just that we have to change the mass. The mass actually changes, and the correct mass is m0 times gamma u. The reason that I prefer that interpretation is because this effective mass, rest mass times gamma u, works in any situation where you might need the mass, whether you're talking about inertial mass, meaning the mass that resists changes in velocity, or gravitational mass. So I think it really makes sense just to think about the mass changing as the velocity increases. Now, if we make a graph of gamma sub u as a function of u, we know what the graph of gamma looks like. It starts out at 1 and it diverges as the speed approaches the speed of light. So what this is telling us is that the mass diverges as the speed of the object approaches the speed of light. And that's one way of seeing that you cannot accelerate any massive object all the way up to the speed of light, because it would require an infinite amount of energy. Okay, thanks for listening.